a triplet state here. For two spins that are anti-parallel, we have the s's cancel, so s is 0, so this is called a singlet state. For the last one here, as a single spin, which is 1/2, means that we have a doublet. It's called a doublet. So these nice configurations are important because they couple the degrees of freedom for the orbital angular momentum and also the spin angular momentum. And we have to remind ourselves that for a non-relativistic atom, we have the spin and the orbital quantum numbers coupling, as we mentioned. So let's refer to a second point. The second point I would like to draw is that if you look at the 2s½ and 2p½ you may say, okay, they are equivalent, they are degenerate levels. But actually they are not degenerate, and specifically when you couple this to the radiation field. When you couple this to radiation field, this degeneracy is eliminated. And this is what I call the lamp shift. So just definition for Willis lamp, a lamp shift. A lamp shift introduced the idea of shifting the levels by some gigahertz. This is 1 gigahertz here. Okay, and this is the ground state or lower energy state is 2s½ and this is 2p². So remember that we have non-degeneracy. Actually, we have non-degeneracy in everything. So do not be just convinced by the idea of degeneracy, because we always, even there is no light, we will see that even we break the degeneracy because of the coupling to the vacuum at some point. Okay, so let me just, before getting to the third point, remind you that for spin orbit coupling I can write down the Hamiltonian for spin orbit coupling as the following. So accept it like this. It has deep definition, but just I get you to the final result. It scales with 1/r³ for some Coulomb fields, and then you will see that scales with r³. And in terms of S and L as components for the spin and for the angular quantum numbers. This is a spin orbit coupling Hamiltonian. Okay, so let's get to the third point, which is considered to be before the last point, that if I have a system, atomic system like this, and I couple to the field, magnetic field, we know that the Zeeman interaction with the atom starts to lift the degeneracy and to raise it to another different levels that we have. And by breaking the degeneracy, even in the magnetic field interaction with the system, actually we have to remember that we have what we call the hyperfine structure limit. We have the finest structure of the hydrogen, like for example, and the finest structure is responsible for coupling the orbital angular momentum with the spin angular momentum. You can see this finest structure splitting in your atomic system. But the hyperfine structure is kind of important because it couples the degrees of freedom for the nuclear spin and both the coupling for J, the coupling for L and S. So now the nuclear spin plays an important role, which drives what we call the hyperfine states. So you would break the hyperfine state into two states. Remember, or kind of history, that this history refers back to the maser for hydrogen. Okay, and this level, or these levels, are separated by around 1420 megahertz. This is responding for around 2.5 or 2.1 centimeter for hydrogen. So now we have finest structure and we have hyperfinest structure. You will see hyperfine levels so much in the history of atomic physics, and even when you drive transitions and even start to cool atoms, you will see those hyperfine transitions, hyperfine couplings like this. The last point, which is that now we don't have only the spatial part of the wave function, but we have also the spin part of the wave function. So you have the spatial part here, and you have the spin part, which are labeled by S here. So in terms of, you have, for example, symmetric wave function, we have antisymmetric, spin wave function. If you have symmetric spin wave function, we have anti-symmetric spatial wave function. They are kind of anti-parallel to each other. So the wave function can be written not only for the, like what we are used to be doing in the quantum mechanics courses, that we have the spatial part, but we have also to include the spin parts of this spinner with the spin eigenstates of our quantum system. Thanks for watching this video, and let's begin our journey in quantum simulation from the next video and start to build this upon higher levels.